Welcome to BE544. In the previous lecture, we have covered the meaning of convolution neural network and how to build an architecture or a network using it. We understood and knew the meaning of each layer, like conv layer, max pooling, or in general pooling layers, and also activation functions. We used Keras or TensorFlow to build our first architecture using CNNs, and the next step is to start training the model on your dataset. But first, let's recap some points. In classification, there are two types, binary classification and multiclass classification. In binary classification, your aim or target is to classify two categories, let's say tumor cases and normal cases, while in multiclass classification, your aim is to categorize different classes, let's say normal, benign, and malignant tumors. So, in binary, you are targeting two classes, and in multi-class classification, we are targeting more than two classes. And the difference also between them is that in the output layer, you need to use the sigmoid activation function for binary classification and SoftMax for multi-class classification. And the difference between them is like that. In binary classification, we have just two classes, let's say 0 and 1. And by setting the output activation function to be sigmoid, we are squashing the output to be between 0 and 1. And in that case, you will get a probability or a value of the prediction that's between 0 and 1. So in binary classification, the point here is by setting a specific threshold, let's say 0.5, we are declaring if the output refers to which class. This means if the output is greater than 0.5 or equal it, then it will refer to class 1, and if it's below 0.5, it will refer to class 0. That's why we are using sigmoid in binary classification. But in multi-class classification, we have multiple classes, or more than two classes. So we are using the softmax. And simply, the aim of the softmax function is to find the normalized exponential of each output. This means we are getting the exponential of the output divided by the summation of all exponentials for every class. What does it mean? This means is that before the activation function, we have a dense layer which is set to get, let's say, 4 classes or 5 classes, as we handled in the code. So this layer will get some values, which are called logits. And those logits are values. So by getting the exponential of each value and summing it to the summation of all of the exponentials, then we are getting the normalized version of the output. And this is called softmax. And the resultant output, which are the probabilities, will get a summation of 1. So if you summed all of these values, you are getting a value of 1. This ensures also that we are getting the normalized probability. So which class should we select? We are selecting the class with the highest probability. And in this case, we will select that this image refers to a dog. Also, this output means that there is more than 75% probability to be a dog and around 11% to be a cat and below 1% to be others. So you can easily interpret these values and check the confidence of the output or the probability of getting such an output. So again, we are using sigmoid in binary classification and setting a specific threshold, and depending on it, we are getting the output, whether the input refers to class 0 or class 1, while in multi-class classification, we are getting logits from the output layer, and by applying the activation function, which is a softmax, we are getting probabilities, and the highest probabilities refers to the selected class. We mentioned also that there is a loss function, and the aim of the loss function is to find the accumulated loss between the predictions and the ground truth or the actual labels. And our aim or goal is to minimize the loss function. And theoretically, the minimum loss function should be 0. This means that the system predicted all of the outputs to match the ground truth labels. One of the commonly used loss functions is called cross-entropy, and there are two versions of it. The first is called binary cross-entropy, and this is used for binary classification, and we have categorical cross-entropy if you are dealing with multi-class classification, and pose deals with the logarithm. So here we are looping on all of the outputs and calculating the summation between two parts. The first part refers to a specific category, while the other refers to the other category. And we are doing that on all of the values. Let's say we have 10 instances or 10 inputs. We are calculating this on all of the 10 inputs and then normalizing it by dividing by n. So n here refers to the number of instances, I is the index, the summation refers to a loop all over the instances, and y subscript I refers to the actual label, while y subscripted by I hat refers to the prediction. So if you are dealing, let's say, with an instance with a ground truth or an actual label of class 1 with a value of 1, then you will multiply the logarithm of the prediction of this instance multiplied by 1 plus 1 minus 1 will be 0, so this part will be neglected. So simply one of those factors or parts will be selected depending on the ground truth. And for categorical cross-entropy, we are generalizing it by multiplying the ground truth by the logarithm of the prediction of the same instance. And we can also normalize that by dividing it by n to obtain the normalized loss function. Now, let's get an example. Let's say we have got these probabilities for a specific instance, and this instance in this case is the dog in this input image, and we need to calculate the categorical cross-entropy for that instance. What we are going to do is to multiply each value by the corresponding probability. So we multiply 1 by the logarithm of 0.775 and 0 multiplied by the logarithm of 0.126, and the same for others. Summing all of that, we will reach about 0.3677 for that instance. And if we have multiple instances, we will do the same, summing all of them together as shown in the summation here, and divided by the number of instances. So let's say we have 10 instances. We will do the same for all of the 10 instances and divide it by 10 to gain the normalized loss function. Another example, we have the label vector for a specific instance and the corresponding probability. So to calculate the categorical cross-entropy between them, simply multiply each value by the corresponding probability. So 1 multiplied by the logarithm of 0.7, 0 multiplied by the logarithm of 0.2, 0 multiplied by the logarithm of 0.1. Summing all of that, we will get around 0.3567. Again, if you have multiple instances in your problem, do that for all of them, divided by n, which refers to the number of examples or instances. You will get the categorical cross-entropy, which is normalized for all of the data. So to make it general, you are doing that for all of the classes for a specific instance, and then doing the same for all of the examples. Divided by the number of examples, you will gain the total loss function in a normalized fashion. Now you may wonder why we are dealing with the vectors or the outputs or the ground truth with that style here and here. Simply what we did is called encoding, and encoding means we are converting the non-numeric data into numeric formats, or in a suitable format that we can calculate the loss function from them. Imagine that we are dealing with cat, dog as strings or text, then how to calculate the logarithm of a word or the logarithm multiplied by a word. So simply what we are doing is encoding these categories into numeric values. In that case, we can easily multiply, add, or subtract to calculate the loss function. There are two types of encoding. One is called label encoding, and this technique is to convert categorical data into numerical format by giving a unique integer value to each category. So this method is straightforward, and it's efficient for transforming any categorical variables into numeric format suitable for machine learning. And it's recommended to use this technique for ordinal categorical variables, where the ordering or ranking between them has a meaning. For example, Let's say we have classes tall, medium, and short. So simply by encoding them into numbers like 0, 1, and 2, we can simply interpret that 0 for tall, and by increasing the number, we are going towards being short. However, you can use this technique with any type of data. The second technique is called one-hot encoding, and this technique is what we did during our examples in the previous slide. So simply this technique converts categorical data into numerical format, which is also suitable for machine learning, but here we are representing each category with a unique vector by simply creating a vector filled with zeros, and at a specific index, we are setting it to one that refers to the category. What does it mean? Let's see an example. If we have red, green, and blue, so we have 3 categories. So simply, we will create 3 vectors where each vector is filled with zeros, except for a specific index filled with 1. So simply, let's say there's the first category. So the first index will be 1 and all others will be zeros. For green, there's the second, so we will fill it here by 1 and others by zeros. And for blue, the same, this will be 1 at the third index, and this will be zeros. And if you have 5 categories, then you will create a vector with size 5 times. So imagine it like a matrix 5 by 5. Again, if you return it back, now you understand what is the meaning of 1, 0, 0. This means that we are referring to the first class. And the same here, we are referring to the first class, which is dog. And this method is useful if you have no ordinal relationship between the categories. However, you can use it also with ordinal data. So to compare between them, the label encoding assign a unique category value as an integer, while in one-hot encoding assign a column or a vector. Label encoding is useful for ordinal data, while one-hot encoding is useful for non-ordinal data. The drawback of one-hot encoding, it can lead to high dimensionality where many unique categories. Imagine that we are dealing with 1000 categories. Then we will create a matrix with a dimension 1000 by 1000, and this will be high in dimensionality. And to overcome that issue for the large number of categories or classes, we can use label encoding. And also, the disadvantage of label encoding, if you use that with non-ordinal data, then the ordering will have no meaning. So simply, depending on the number of categories and the type of the data or the type of the classes, you can determine which technique to use. Now we discussed what is the loss function and the output activation function that we can use. And let's say that we are ready for the training process. And the training process means that we are going to tune the model or the architecture with the help of the loss function and optimization function to learn on the data and to teach that model the different patterns caught from the data. So before starting the training process, we need to ensure that we are splitting our dataset. And we are splitting our dataset aiming to judge and evaluate the performance of the training process. So simply imagine that there is a student who have learned during the whole course without any examination. Then you will not be able to judge the performance of that student. So what we are doing here for machine learning is to split our data into 2 or 3 subsets. If you are dealing with 2 subsets, then you are splitting the data into training and testing. And if you are dealing with 3 subsets, then you are splitting it into training, validation, and testing. So what is the meaning? The training subset is used for training the model to learn from the different patterns found in the data. So we can consider now that the training subset is seen by the model. And the training process is done over multiple iterations. So we need to evaluate the model after each iteration and after the completion of the training process. So after each iteration, we are judging the performance using the validation subset. So in this case, the validation data is not seen for that iteration, but the model will get the benefit of it for the remaining iterations. So we can consider it also it's semi-seen. At the end of the training process and the completion of all of the iterations, we need to judge the overall performance after that. And this is done by using the testing subset. In traditional machine learning, as many algorithms do not use the concept of iterations. We are splitting our data into training and testing. We are training the machine learning model on training subset, and after that, we are testing on the testing subset. While in deep learning, as we are dealing now with CNNs, there is a concept of iterations. So simply, we are splitting the data into three subsets. The training and validation are injected in the training process, where the model is trained on the training subset and is judged after each iteration on the validation subset, and after completion, the model is examined and evaluated on the testing subset. And the ratio of splitting differs according to the size of the data. So let's say that you have 1000 records or 1000 images. So you can use a ratio of 70 to training, 30 to testing, or if you are splitting it into three subsets, you can use 70 and 15 for validation and another 15 for testing. But if you have a large volume of data, let's say 1 million images, then you need to consider carefully the ratio, because 1% differs from 15%. So for larger volumes, try to decrease the percentage or the ratio of validation and testing subsets, making it, let's say, 1% or 2%, while keeping the remaining for the training. There is another approach called cross-validation, and this approach is very useful if you are dealing with a small data set. So simply in cross-validation, you are splitting the data into what's called k-folds, where k is determined by you. So if you are dealing with 5 folds, then you are splitting the data into 5 portions, where k-1 will be used for training and only 1 will be used for testing. And you will repeat that over multiple folds and accumulate the output and average it to get the result. To understand it, let's see this figure. For the train test split, as mentioned, we have the full data and we are splitting it into 3 partitions. Let's say 70 for the training, 15 for the validation, and 15 for the testing. And for cross-validation, we have all of the data. Then first, we will split it into the training data and testing data. Let's say we will take out 15% from the whole data to be for the testing subset. Now let's focus on the training data. Let's say we are using 5 folds. So we will split the data into 5 folds from 1 to 5, as you see. And you will repeat the experiment 5 times, where 5 is the number of folds, where in each split or in each experiment, you will take k-1 for training and 1 for testing. And for the second split, you will change the index of the testing subset, where in this case, this will be for testing and the remaining for training. And for the third experiment, you will take, for example, the first 2 and the last 2 for training and the middle for testing. Upon completion of the 5 splits or 5 experiments, you can evaluate all of them by getting the average of each experiment. And at the end, you can evaluate it on the testing data. And as you see, the testing subset is unseen to the model in the different phases. Now, after understanding how to create a model using CNN by cascading the different layers like conv, pooling, and dense layers, and getting familiar with the meaning of loss functions and how to calculate it for binary and multiclass classification, and the benefit of setting a specific activation function depending on the type and the number of classes, SoftMax for multiclass and Sigmoid for binary classification, and also getting familiar with splitting the data and the type of splits. Let's combine all of that together in a single script. In this script, we have imported the different packages: NumPy for numeric operations, Matplotlib for visualization, TensorFlow for building and training the model, scikit-learn for the model evaluation. First, we printed the version of the GPU, which refers to the graphical processing unit, and it's recommended to train a deep learning model on a GPU rather than a CPU to get the benefit of parallel processing and to decrease the consumed time in the training. Here, we use the same architecture as we did in the previous lecture, but we added it into a function called simple CNN, where this function accepts the input shape, the optimizer, and verbose if you need to print the architecture of the model or not. First, in this function, we created the model, and in the input shape, we used the parameter input shape. So this function can be useful if you need to change the size of the input. Then we used the compile function, where it accepts our optimizer and the type of the loss function, and in our case now it's categorical cross-entropy, because we are using multiclass classification. And if you are using sigmoid and have binary classification, then you can use binary cross-entropy. There is another type called sparse categorical cross-entropy, and you can use sparse categorical cross-entropy instead of the categorical cross-entropy if you are encoding your labels using label encoding. If you remember from a while, we mentioned that there is a difference between label encoding and one-hot encoding. Label encoding converts the classes into unique numeric values, and if you did that, use a sparse categorical cross-entropy. But if you used one-hot encoding, where we are changing each class into a vector, then use categorical cross-entropy. Then we used metrics, and these are the reported metrics during the training process. So we are reporting accuracy, precision, recall, and others. And we are going to understand the meaning behind them also, and how to calculate them in a future lecture. We used the verbose so that we can optionally print the model summary or the architecture, and at the end of the function we return the model. So now we can call this function at any location to get the model which is ready now for the training. But before the training, we need to load the data and prepare it well for the training process. And preparation means you can apply different pre-processing techniques, such as resizing the images to make it in a unified shape, splitting them into training and testing as discussed. So first, we defined the different configurations: the input shape, batch size, number of epochs, samples per class, and input shape, we knew what is the meaning of it. It's injected to the simple CNN function and set in the input layer. And let's skip those for now until we know where can use them and what is the meaning behind them. Next, we defined the base path, and this path refers to the path of the dataset. Then we created a list of the different categories: benign, carcinoma, and normal, and those categories and names should match the same classes and names as in this folder. Then we started loading the data. How we did that? First, we created X and Y as empty lists. X refers to the images, Y refers to the labels. Then we created a loop to loop all over the categories, and simply what we are going to do here is to get the first class and get the different images inside this class and start reading it as vectors or matrices and appending it to X, where X will carry all of the images. And in the same way, we will read the category and append it to Y, which refers to the labels vector. So first, we obtain the different files inside this category and selected only a specific number of examples inside from the files. How we did that? Using random choice, and it will choose only this number, and we set earlier this number to be 300. So the loop will only load 300 cases or examples from each class. Then we are looping on each file, reading the file, resizing it to the input shape, which is set here, so that all of the images have the same shape, to avoid any exception, just in case if one or more of the images has a different shape than the set one. Then we appended both the image in X and the class name in Y. Now we are ready with the data and the corresponding labels. Next, we are applying what is called normalization. And the normalization here helps to avoid an issue called overfitting and helping the model to converge to the best loss function easily. So instead of teaching the model on the actual values, which ranges from 0 to 255 because we are dealing with images, whether it's gray or colored, we decrease that range or domain to be between 0 and 1. So any mathematical operations or convolutions that we applied on the images will be applied on the small range rather than the wide range. And imagine that we applied it on the wide range, which ranges from 0 to 255. Then inside the architecture itself, it will deal with those large values, accumulating at the end of the architecture with a very large value, which may overflow your memory and getting wrong results. So here, if you are dealing with images, it's recommended to normalize it by simply dividing it by the maximum value, which is 255. Then we are applying encoding. And as mentioned, we need to use one-hot encoding, as we are using here categorical cross-entropy. And this is done by using the function toCategorical. And this function accepts the y vector as numeric values. But if you remember, here we are using strings or text. So simply what we are going to do is to use the label encoder first and convert them to one-hot encoding. So the label encoder will convert y from string to unique numeric values, and the toCategorical function will convert from these unique numeric values into one-hot encoding. Then we printed the different shapes on the command window. Then we created the model by passing the input shape, the optimizer, which is Adam in our case, and silverpost to 1 to print the summary or architecture. Then we started to split the data into training and testing. And we did that using the train test split function. It accepts x and y, the size of the testing, whether you need to stratify or not, and the random state. If you need to apply randomization, you can change this number in every experiment. The meaning of stratify is simply to split the data equally between the classes. So by applying that, you are telling this function to ensure that for each category, just get 80% for the training and 20% for the testing. And by doing that all over the classes, then you are ensuring that 80% from every category are extracting for training and the remaining 20 for testing. Because if you didn't apply that, in some cases, you may get different ratios. It may get from the first class 95 and the remaining 5 for testing, 50 and 50, 70 and 30 for testing, and different ratios, because it simply treats all of the instances as the same. Just picks 80% from the whole dataset and 20% for the testing, regardless if they refer to a specific class or another. So, as a point, it's recommended to apply stratify so that you are ensuring that you are getting the same percentage in all of the classes. Next, we are creating the history directory, and the history directory will store the results. Then, we are using the fit function to start the training process. And the fit function accepts the training data and can accept also the validation data if you have. But if you don't have validation data, you can ask the fit model to split internally the training data into two portions, one for training and one for validation. And this is the ratio. It accepts also the argument epochs, and it refers to the number of iterations. And the epochs here in our example is set to 200. So we are training for 200 iterations. And in deep learning, we call it epochs. And batch size argument refers to how many portions in each iterations do we apply forward and backward propagation at one time. So simply, here we are telling the model to use 64 at one time in forward propagation. So instead of applying the whole data as a whole, as it may not fit the memory, we are dividing it into portions for each iteration. So in the first iteration, simply it takes the first 64 images and apply forward propagation to calculate the loss function, and the next another 64, and the same until we complete the whole dataset. By doing that, we are relieving the memory and avoiding crashing it. And the choice of the batch size value depends on the data and the problem. You may increase the batch size and get poorer performance than decreasing it, and vice versa. So it's recommended to try different batch sizes and obtain the one with the highest performance. Next, we are using the argument callbacks, and simply callbacks are functions which are executed after each iteration. That's why it's called callback. We are using ModelCheckpoint, and this callback tries to pick the best model among all of the iterations. So let's say we are iterating for 10 iterations. So this callback will test if this iteration is better than the previous iteration or not. If so, keep it as the best checkpoint. If not, ignore saving it and storing it as the best checkpoint. It will do the same for all of the iterations, aiming to find the best checkpoint among them. The next is called EarlyStopping, and EarlyStopping simply stops the training process before completing the total number of iterations. And we are doing that when the model stops improving. So let's say the model stopped improving after the 10th or 11th iteration. So it's not necessary to complete the whole iterations, which is 200, but we can stop earlier. So when to stop? Simply by using the patience. So the patience is 50, means if the model didn't improve in the next 50 iterations, then stop the training process. CSV logger, simply it logs the training and validation performance. So it will log all of those metrics alongside the loss function for the training and validation. Reduce learning rate on plateau, and simply it will reduce the learning rate when the model stops improving. So it detects during a window of 10 iterations. If the model didn't improve, then it will reduce the learning rate, aiming to find a better performance and emphasizing and encouraging the model to improve. The tensor pool is another callback, and we are going to cover it in the next lecture so we can see it visually. And verbose, simply it accepts 0, 1, and 2. 0 to stop verbosing and stop any output from the training process. 1 and 2 refers to getting an output from the training process, whether you need to get an output after each batch size or after each iteration. And the output will be the performance metrics alongside the loss values for the training and validation. Now, after the completion of the training process, now the model is ready, and you can access the best model from the checkpoint. Also, the fit function returns the history, and the history contains the history of the training and validation all over the number of epochs. At this point, we have a tuned model. So you can load it using load weights, and those weights are the highest or the best as it's stored by the model checkpoint. Now you can use the model which is tuned to make any further predictions. You can use the evaluate function to evaluate the performance of your model, and the result here will be the metrics and the loss function, the metrics which are set here. Stored in the order of the loss value will be the first, followed by other performance metrics ordered as the same order as here. So this function will take x and y, which for the first iteration will refer to the training, and the second iteration will refer to the testing, printing them on the command window. Then we are plotting the history, and here we are plotting the loss for the training and validation, and the accuracy for the training and validation, and storing them as an image. We can also use the prediction function, and the prediction accepts only x and report the predictions. And this function is useful in the inference phase or in your application where the actual label doesn't exist. So there's a prediction. Now we have the predictions and the ground truth. Based on those, we can create what is called confusion matrix. And this confusion matrix creates a matrix of n by n, in our case 4 by 4 because our classes are 4, where it accumulates the number of correct predictions and misclassifications and sets them in the corresponding place, as we are going to see. And the function confusion matrix display, it displays the confusion matrix as a figure. So when you execute the code and complete the training process, you will get first the training and testing performance, and second, the training and validation losses and accuracy curves. Let's first interpret the curves. The top one refers to the loss training and loss validation, while the second one refers accuracy for the training and validation. And as you see here, the training accuracy is in blue and the validation accuracy is in orange. And you can interpret that the training accuracy is increasing until it reaches 60, for example, until the remaining of the epochs, or if the early stopping is executed. And here it settles at around 85 or 90. While for validation, it settles only at 45 or 44 in accuracy. And from both of them, you can say that there is a wide gap between the training and validation. And in such cases, this is called overfitting. And overfitting means that the model is training well, but it doesn't predict well. So our goal is to learn the different techniques of moving that curve from here to be closer to the training curve. And in such cases, this is called a fitted model, where the training and validation are close together and high. And if you found that the validation curve is higher than the training curve, this means it's underfitting. And this for the accuracy or the recall curves. While for the loss curves, it's different, because in the loss function, we need to decrease it, while in other metrics, we need to increase it. So simply, the training is decreasing, while the validation started to decrease and then increased. And also there is a big gap between them, and this is also called overfitting. This is also reflected in the metrics. For example, for the accuracy, 81 for the training, 49 for the testing. There is a wide gap between them. This is called overfitting. So we need to learn how to decrease this gap, to reduce overfitting and increase the performance, whether by increasing the data, adding more layers, changing the architecture, changing the hyperparameters of the architecture, and so on. And this is what we are going to learn in the next lectures. Also, for the confusion matrix, you can interpret them simply as mentioned. It's 4x4 matrix, n by n, and n is 4. Here are the true labels, and here are the predicted labels, organized in the same manner, starting from benign until normal. And our aim to gain the diagonal to be the highest values. And the diagonal refers to the correctly predicted instance. For example, here, there's an intersection between benign as an actual and benign as a prediction. So this number is correctly predicted to be benign, while those numbers are misclassified. They are predicted to be other categories other than benign, while they are actually benign. And for those, they are predicted to be benign, while actually they are other classes. And this is how you can interpret the confusion matrix. Also, you can say on the instances that are correctly predicted to be true positive, because they are truly predicted to be that class. And for the instances that are predicted to be other than that class, they are called false negative. Negative means other classes, and false means misclassification. And here are false positive, because they are predicted falsely to be that class. And others can be assumed for that class to be true negative, because they are predicted to be other classes, and actually they don't refer to the current class. So now we have 4 values: true positive, true negative, false positive, and false negative. And now you know how to interpret them and gain those values. And we reported that in our matrix. There's a true positive for all of the classes, true negative for all of the classes, and the same for others. Those are for the training and those are for the testing. So in this lecture, we have covered the difference between binary classification and multi-class classification, and we reflected that in the output activation function and the loss function. Then we went through the encoding process, and we differentiated between label encoding and one-hot encoding. Then we covered the splitting by covering train test split and cross validation. Then we reflected all of those in our script by knowing how to build the model, then read the data, reprocess it, making it ready for the training, then starting the training. And once the training is completed, we can use the evaluate function if we need the evaluation, and we can use the predict function if we need the predictions as a value, just in case if we don't have the ground truth and we need only the prediction of the tuned system. We covered how to interpret the learning curves and the difference between fitted, underfitting, and overfitting. Also, we covered how to interpret the confusion matrix, and our aim in all of that is to gain a model which is tuned with learning curves close together and reaching a settlement at a high value.